Okay, well, we'll go ahead and have a soft start. Welcome, everybody, to the Central Florida Astronomical Society. I will, don't worry. She taught me how to say it. So, do we have any new members that we can recognize tonight? New members? Yeah, Lori, stand up. Welcome, everyone. Any first-time visitors that we can accost afterwards? No, not really. Great. How did you hear about CFAS? Website. Okay, very good. Google does work. Thanks for joining us. How about this group over here against the wall? Facebook. No, it's up there. That works too. Well, welcome. Do you want to tell us anything about yourself? No, that's okay. It's like in church when they say, well, while everybody's eyes closed, raise your hand. And they say, okay, now come up front. Thanks. All right, so what's going on in astronomy lately? Everybody repeat after me. Betelgeuse. Yeah. Betelgeuse. Betelgeuse. So,
and the thing they just announced today about 80 years, there'll be a star that'll go supernova.
In 80 years?
Francisco.
A star or Betelgeuse?
Isn't it Sagita?
That would be awesome. I was quite certain.
It's supposed to be brighter than Venus.
I was quite certain Betelgeuse was going to go off this weekend because my mother called me with no notice and said she was getting married and I had to drive for 2 days there and 2 days back without any of my equipment. It was like, for sure, it's going to go off this weekend. I would have put real money on that. I did do a little homework about Betelgeuse. For those who don't know, it is actually a variable star and typically varies from magnitude 0.2, which is roughly the same as Rigel, to about 1.3. And in December, it was down to 1.5, which is pretty dim. It fell from the 10th place to 21st place as far as brightest stars in the sky. And it is a pulsating red supergiant. Is it about to go supernova because it's the dimmest it's been? It is the dimmest it's been in recorded history since we started recording. So surely this means it's going to go supernova. Actually, the standing explanation is that there are numerous cycles that it goes through dimming. There's a, let's see if I get this right, there's a 425-day cycle where it dims and brightens, and there is a 5.9-year cycle where it dims and brightens. And of course, those two cycles just happen to overlap, where they're both dimming at the same time. So what we're seeing is actually pretty normal, just rare. So it doesn't mean it's doing something really unusual. The math actually works out, so it is doing what we think it's going to do. Now, let's see what else I have highlighted here.
But the time what we see now is about 1600.
It is 1,600 light years away, so it may have already gone pop already. It is likely to go supernova any time in the next 100,000 years.
Yeah.
And that's any time. It's like playing the lottery. Tomorrow is just as good as next week.
But they did the calculation in the Netherlands. I heard that they say the maximum time will be 400,000 years.
They think it'll be so between 100,000 and 400,000. Okay. So it could go off in the next 100,000, but it might be as late as 400,000. So apparently there are traffic jams in space too, and it might be late. All right, so they call it a super minimum. It's just what we need, right? Like another super moon. It's a super minimum because the two minimums overlap with each other. I see Julie's here. Yeah, our speaker's here. Yay! We're glad you got here safe. We heard there was an accident.
Yes, there was.
That star is B Sagitта, and it's a binary. And they say that in the year 2083, the white dwarf will suck in its companion, and it will go.
In 2083.
2083.
Okay. I'm going to have to Eat well and exercise, yeah. I remember, somebody correct me if I'm wrong, there was a supernova that was calculated that did go off on schedule. We did predict a supernova pretty close.
You're talking back in 1987?
I'm talking about sometime in the last 20, 30 years or so. I remember seeing that. Of course, just because it's on the news doesn't mean it's real. We all know that, right? But it seems like I remember seeing a supernova that was predicted.
Like I said, it'll be brighter than Venus.
Brighter.
No.
As bright
I
as a
remember
full
a
moon. I think.
supernova that was predicted, and it did go off as predicted. So somebody's math model was working correctly. But I don't remember the details. I just now remembered it standing up here because he said there's one going off in 2083. All right, renew my gym membership. Francisco? Telescope? Oh yes. Do you want to say? We are missing a telescope. Does anybody have a Lunar 8-inch Dobsonian Skywatcher?
It looks like that one, but it's white.
Yeah, it looks like that, but white. Until it's found, nobody leaves this room. He's got his camera. All right, well, keep your eyes peeled if you know any other members. We don't necessarily want to take it away from them. It's one of our loaner scopes,
I
but
just want to account for it.
There was-
It was loaned to somebody without going through my hands and for an outreach event, and now
there was a paperwork snafu that won't ever happen again, but
we don't
it did
know
happen,
that.
so. Yeah, we-
Remember those days?
yeah, in the dark, late at night.
Who's
Yes.
collecting the funds for the Star Party?
Okay, so between the main speaker and the mini program, we're going to talk about AstroFest, and we'll have a break, and I'll be collecting money for AstroFest. So we're going to do that. We won't make you stay through the whole program for that, but we'll do that. We'll do that later. The other thing I want to talk about before introducing our main speaker is how many of you don't raise your hand. This is rhetorical. How many of you hate Facebook and refuse to get on it? Okay, just rhetorical. All right, so the board recognizes that as a valid concern, all right, because we're not stupid, all right? We know good and well that we're giving away when we get on Facebook. A number of members, more than just one, has brought this up in the past that our main means of dissemination is Facebook. Facebook is a really robust platform. It's really great. We don't want to have to build something ourselves. We have a website, but getting people to come to the website and maintaining it and keeping it from getting hacked is a gigantic responsibility and a full-time job in and of itself. And we're not going to do that. It's just not going to happen. So we need something nice and put together and commercial like Facebook, except it doesn't, suck up your soul and all your privacy information. So we are looking into some alternatives. The top contender right now is Groups.io. If anybody has any suggestions or something better, now is the time to speak because we're going to move on it pretty quick. But we think Groups.io is a really good, maintains privacy, it's nice commercially maintained, so we don't have to worry about spam and all that. We get all of that. Does everybody have email? I mean, pretty much you have to have email. We got to draw the line somewhere. If you don't have email, we're not going to be able to get a hold of you electronically. So we're not going to make you get on Facebook, we're not going to make you get on Google, but we will. It's going to be kind of, if you want to know what's going on and you want to get notified, you're going to have an email address and you'll have to give it to us. Okay. So, yeah, so there's that. I meant to bring that up at the Christmas meeting. Yeah.
Have you guys looked at Group?
Groupie?
Group Me?
Group Me?
Yeah, it sounds like it's probably similar to whatever you're looking at.
No, I haven't heard of that. Did we talk about it? Yeah, Groups.io seems a better one. My favorite was Slack. I use Slack all the time, professionally. It's a really great collaboration tool, but it does. Yeah, Groups.io just seemed like a better fit for us. Okay, well, yes.
I have money to give away.
You have money to give away.
Yes, if you're the treasurer and you're collecting dues. So who is that?
The treasurer could not be here tonight. That's Ken. But you can probably give that to our membership chair. Where's Eric? Eric Martin, we'll pin him down later.
Okay.
Yeah. See Eric Martin about that.
I wanted to do it publicly because the last 2 years I wasn't Marcus Cave.
Oh, okay, so all right, great. Public, no, it's even recorded now, so, all right, very good.
No exchange of money yet, so it's not recorded.
No, it's true, it's only intent.
Yes.
All right, so, when we have a guest speaker, we usually let the guest speaker go first, so they don't have to stick around for all of the exciting stuff that we talk about other than the main program. And I'm not going to introduce her. I'm going to let Anna Metke introduce her because Anna knows her well and recommended her. There you go, Anna.
All right. So this is Dr. Julie Brisset. She is one of my favorite people. She's an incredible scientist. She has a lot of integrity and does a lot of good work. She's a really good leader, and she's a great mentor for all young of us. And most importantly, though, I will say she is hilarious.
Thank you very much.
Thank you. Great introduction. Private joke there, of course. I'll try to not be too funny tonight. Okay, so thanks for inviting me. It's a great pleasure to be here tonight. Please remember, I'm originally a physicist. And so it's possible, very possible, that many of you in this room tonight know more about, actual astronomy and where the stars are exactly than me. So please don't be mad at that. All right, so tonight I'm going to talk to you a little bit about some work that we're doing at the Florida Space Institute. So this is part of the University of Central Florida. We're a research institution, and there we have some activities relating to space, and in particular dust for me. And part of that work is looking into the very first stages of planet formation. So in the beginning, there was dust, and maybe that's where we're going back. But how did these planets form from these dust grains? So that's a little bit what I'm going to be talking tonight, with some illustrations of how we investigate that experimentally a little bit at the Florida Space Institute. So we first start with a little bit what we think these days, the early stages of planet formation look like, what happens there, and then I'll show you a couple of microgravity experiments that we do on the topic. I'll talk about one in particular, the Nami Rocks experiment, and then some of the data results, and then finally how this data can go back to help us understand how planets that form in the very first stages. All right, let's get started. So planet formation, we have a pretty good idea that this happens in these disks of gas and dust that are around young stars. So this is the Orion Nebula here, and there's a lot of these cradles for future stellar systems. So we see these. So these are Hubble pictures. So there was a very nice IMAX film, by the way. I don't know if you got a chance to see that. That was doing a rendering of 3D voyage through the Orion Nebula, going through and close to these disks. So these protoplanetary disks, this used to be the images that we had with Hubble. So there is a star in the center. I hope it's not that strong. All right, anyways, to the right, you can recognize a little bit the star, but it's very darkened by the disk around it. This is a thick gas and dust disk, and the dust in particular is what darkens it like that. So these used to be the Hubble pictures, but now we have very nice interferometry telescopes for millimeter and centimeter wavelengths. For example, this picture was taken using ALMA, the Atacama Enlarged Millimeter Array in Chile. And here what you see is actual structure. Ooh, this works now. So this is the central star, a young star, and then you see the structure in the dust disk around it. So previously with Hubble we could just see, okay, there is a dust disk. Now with this millimeter array, we see the structures, there's gaps, there's rings, and this is where the planets are forming from the dust grains. There is also, so here I put a couple more because they're just beautiful. So a lot of structure you can see the spirals, you really see gaps. So these are in formation planetary systems.
How far across it?
700 AUs. Yes. So, yes. And so another one that works well is a very large telescope. It's also in Chile. So there they're also getting very nice pictures. In particular, you can see here, for example, this is a protoplanet. The first image protoplanet, really, that we're seeing it form right there. All right. So this, in the last couple of years, has been taking off really well, looking at these planetary systems being formed. So the question that we're interested in, so the dust in these disks typically has the size of a micrometer. And our question is, how does this dust grow into planets that have the size that we think, now we see all the exoplanets, but the sizes of planets, for example, like in the solar system, or the sizes of planets that we see in other exoplanetary systems. So how do we get this growth? And well, the initial thought is just, okay, it's just agglomeration. The grains in the disk, they aggregate, and then they grow, and until at some point they reach the kilometer size, so that's about the size of an asteroid, for example, and then they start having their own gravity, and that's basically another problem. Now gravity interactions, the growth proceeds through accretion, and then for gas giants, that happens fast enough for the gas giants to collect the gas that remains in the disk. So this was the idea. So there's first growth phase, that's aggregation, and then gravity takes over to form the planets. And so to a certain extent, for very small grains, this actually works really well. That's called the hit and stick behavior. So of course, there was a theory, so people thought, let's do some experiments. So here, for example, some micrometer-sized grains were put together in a gas flow and were observed aggregating due to Brownian motion in this gas flow, and you see it sticks immediately upon contact, and it forms these nice fractals. So very small particles for very gentle collision speeds, which is expected in a disk for these small particles, they just hit and stick. So that works.
Electrostatic?
So yes, upon contact. So it's basically van der Waals forces. Even if the grains are really grounded and neutral, upon contact you will have surface forces, dipole forces that will lead to the sticking. The smaller the grains, the better it works. So surface forces lead to sticking. So that works well, and here I have an example of an experiment where we actually reproduce that. Okay, so of course it's in a cell, so you have to contain it somehow. But you have a nice behavior where upon collision you have a sticking. And you grow these fractal aggregates. This one is more compacted than this one because it has regular collisions with the cell walls, which compacts the aggregate. But you have a nice hit and stick behavior.
Is that in a vacuum?
I'm sorry?
Is that in air or?
So that it was in vacuum. Yes, vacuum and microgravity, so that you can reach very gentle collision speeds. Problem with gravity is it will accelerate everything. So in order to reach the gentle collision speeds that we expect for these small particles in the disk, we go into microgravity. This specific one was in the drop tower in Germany. It's 100 meters high, and they have a catapult system. You get 9 seconds total. So what you saw was about 4 seconds, and it aggregates really efficiently. So that works well. But of course, as usual, it's not that simple. There is a problem. So the particles are growing in the disk, and the bigger they get in the disk, the faster their relative velocities are going to be. So they're going to be larger, and they're going to bump into each other faster. So the mechanisms that lead to particle collisions are differences in the speeds of the particles. So when you have very small particles, they're very well coupled to the gas, so they follow the gas, and so they're very gentle collisions relative to each other. When the particles grow, they start decoupling from the gas and they start having Keplerian motion relative to the star, the center star. And so now other particles that are still coupled to the gas might have much higher relative velocities. And so as the particles grow, you see higher collision velocities. So smaller particles, the collisions are very gentle, there you're going to have hit and stick. Particles get larger, collisions are going to get more violent. Larger particles, more violent collisions, you end up not really having sticky. All right, now I gave it away. Anyway, these are relative velocities expected in the disk for the grain size. So here, for example, for 1 centimeter grain will have a relative velocity that's in the 3 centimeters per second, compared to here, the micrometer grains, they have really 10 to the minus 2, so that's 100 micrometer per second collision speed. So gentle speeds for small particles. As particles grow, we expect larger speeds upon collision. And so when we do the experiments for larger particles, can someone click on that video? Maybe I have to go back in the back. Sorry, there's going to be a lot of that. Maybe I should. Sorry about that. I'm working very video based. Sorry.
Yeah, I think it's from the presentation.
Sorry,
No problem. Is that Spotify and access? You want me to turn it on?
Alright, let's see. Well, let's see. Alright, so this is actually playing. So it says after the collision though. Alright, so these are 2 centimeter sized dust aggregates that were prepared, and you see they're colliding. So now this is very gently, this is a couple of centimeters per second. So still very gentle collisions, but due to the size of the aggregates, they're not sticking, they're bouncing off each other. Let's see if I can actually go in presentation mode and it will still work. No. Okay. Oui. Sorry. All right, another one. Okay. Sorry, I thought this would work. All right, so now this is the same 2 centimeter sized aggregate. So these are made of like micrometer grains. And now they're colliding at a meter per second, and you see you have fragmentation rather than actually sticking to each other. So you can have bouncing and you can have fragmentation, but at these sizes you don't really have sticking anymore. So let's say you're forming these large aggregates in your disk. How do you continue growth? So this is a problem, because if we now go back to, and if we simulate this numerically, we see it too, and we see also in particular, so here we simulate these experiments that we had just now. So these are 20 centimeters per second, you have bouncing, and you can also simulate much fluffier aggregates if you want it. Just, can you please just do, thank you. Alright, I have them all playing. So you can simulate much fluffier aggregates, and now you see that if the aggregate is fluffy, it actually sticks. Just restructures a lot. So that's a meter per second. That's 5 times faster than just now with the balls.
Is that due to surface area?
Yes, so that's due to how your fluffy aggregate is able to absorb the energy of the impact. So because you have all these vibrational possibilities, you're able to dissipate more of this collision energy compared to, and you are able to restructure, so you lose energy by rolling the grains, by twisting the grains around each other, instead of, if you have very compact aggregates, then there is no chance for the energy to go anywhere inside of the aggregate, and so you have a bouncing off. So here you see that the fluffiness of the aggregates really plays a role. So it's a complex matter.
So it kind of interlocks, right? In a way.
You know what? It's moving the picture. I'm sorry?
It kind of interlocks. When they
Yes.
collide, they kind of interlock with each other a little bit.
Yeah. But now if you have the same fluffy aggregates, and now it's 5 meters per second, so again, 5 times faster, this is too fast, there's too much energy, you're still going to lose most of your aggregates, regenerating small grains. So what happens upon collision to your aggregates, it depends on a lot of factors. And if you do your experiments, your simulations, you get something like this. So this is in the disk. At the bottom here, you have the time. Let me see, sorry, the mass of the grains, the video is gonna play the time. And here's the fluffiness of the grain. So how compact they are. So if the fluffiness, here you have very fluffy grains. As they grow, they become somewhat more compact. Or actually, sorry, these are fluffy grains, these are compact grains. So they grow, they grow, they grow. They become more fluffy. So this is a simulation. And then they reach a point where there is no more growth, really. You're not going further to the right. Instead, you're bouncing off each other, and you're compacting. And this is called the bouncing barrier. Another picture that one can see nicely, this bouncing barrier. So if you start considering that the grains don't necessarily stick to each other anymore, and now I can go back in the slideshow. Here's a plot at the bottom, is the time, and here's the mass of the average grain in the disk. So you have small grains in the beginning, and you start growing them, they grow, they grow, they grow. And then you reach the barrier where they start bouncing off each other and fragmenting instead of growing more. And now your growth stalls and you're unable to grow larger bodies than the millimeter or centimeter sizes. And that's a problem because we see planets. So somehow nature did that. And we're stuck there, not able to grow these aggregates further than the millimeter or centimeter range. So it's unclear from, let's say, the centimeter range to the kilometer range, how exactly this happens, and that's where we're focusing our research on. So really the question is, how do we get from a millimeter, and these are real chondrules from meteorites, to the planetesimal size, which will then take over with the gravity and grow through accretion.
Question.
Yes?
Do you know about the temperature, the impact of the temperature?
There are experiments done, so we're looking usually at 1 AU in the disk. And at 1 AU in the disk, we have temperatures that we expect, let's say temperatures similar to room temperature, let's say. We make our life easier in experiments like that. But we expect that closer to the star, you will have more hotter aggregates, more molten that could sinter, possibly if they were exposed to colder temperature later. And you do expect in the outer solar system that ices will play a role.
Yeah, because when you look to the surface chemistry articles, you see the same type of things forming by dust also on Earth, but also in volcanoes and things like that. And then the temperature is very important, what for type of particle size, how it can be combined to other particles. So my question is, we must be very careful about the particle size you can create, because it is very depending on the temperature in the system.
So we actually don't really see that, in the sense that so lots of experiments were done with different minerals. So these are actual chondrules, but in the experiments different minerals were used and different temperatures were tried also. But if you stay in the mineral world, actually it turns out that the behavior is pretty similar from mineral to mineral, and if you don't go into the melting temperatures. The behavior is very influenced by the presence of ices, for example. Like if you get into colder temperatures, you're going to have a lot of water ice present, or CO2 ice. These ices, they play a very important role in the different stickiness of the material. Another thing are organic components. When you have a coating of organic components, that increases the sticking behavior a lot. But for minerals, so in the 90s, these experiments were started, and they tried to look at like different types of minerals, and it turns out that with like minor factors here and there, the behavior is about the same. And so also, yeah, they did some temperature, like hotter temperatures, but if you don't go into the partial melting, it doesn't really play a role. But these chondrules in particular, anyways, there's another mystery about the chondrules, but I'm going to talk about this today.
Are the volatiles in there? There are volatiles in the planetary disk, right?
There are volatiles in the planetary disk.
Can they have a frictional effect?
So the gases in general, yes. Yes, so there's a lot. So in the beginning, and that's a phase where we are at, there is the gas, and the effect, the most important effect of the gas is to create friction and to create relative velocities between the grains. If there was no gas, you would have a more stable disk like Saturn, for example. But the presence of the gas, it basically induces, the gas rotates subcapillarin, it supports itself by its pressure. So the gas is a bit slower than a body that would not feel the friction. So a body orbiting would go capillarian, the gas is slower, so anything that couples slightly to the gas is slower. So it creates these relative velocities between the grains. So the presence of the gas is very important for this first stage. If there's no relative velocities, there's no collisions, no growth. All right, so the experiments that we're performing are trying to map. Now we're trying to understand, when do we have sticking, when do we have bouncing, when do we have fragmentation. And this is supporting other scientists that then need a recipe basically to simulate an entire disk. So we're not the ones producing the baby planets basically, but as experimentalists we produce experimental measurements that will help these other scientists to simulate an actual disk. So here, for example, in this plot at the bottom, you have the velocity at which the grains are colliding, and here is the size of the grain. And so if you're slow and small, you have sticking, as I showed, but as you start growing in the disk, you become faster, you have faster relative velocities, and so you transition into this bouncing regime. And for very fast velocities, you always have fragmentation of your grain. And so, and all these boxes are like experiments that we've been performing, and we've actually been exploring a bit more down here just to check how our model does. And so here are the microgravity platforms. Earlier I mentioned, oops, wrong button. Sorry. Earlier I mentioned the drop tower in Bremen, so that's it. So they have a catapult at the bottom. It launches your capsule, which then is in free fall for 9 seconds. You have the airplane, there you get about 20 seconds, several times in a row. You have suborbital rockets, there you get on the order of a minute, so 3 minutes for smaller rockets. You can get up to 10 minutes for very large rockets. And then the ultimate platform is orbit. So if you can make it to low Earth orbit, you can have years of microgravity. So classically, this would have been the International Space Station, but we also, and I don't know if I put it there, we now have endeavored to build our own small platforms as in form of CubeSats to go on orbit with our mini labs without having to go to the International Space Station. Here's a summary of the advantages. So the drop tower, you see, microgravity quality is really the best because they evacuate the entire tower. There's no air friction. But then parabolic flights and suborbital rockets, they're medium quality, and the International Space Station, also there you have to live with the astronauts doing exercise right next to your experiment, so there's also a lot of vibration. So the microgravity is, all right.
I have a question.
Yes.
For the actors who, like Tom Hanks in Apollo 13, they do the parabola to understand what weightlessness feels like, right?
Yes.
Yeah, okay.
Yes, on the airplane, this is the only platform for now where you can go yourself. I hear Blue Origin is planning to fly some people this year on their rocket, so. Alright, so I had to exit presentation mode again, sorry, to play these videos. So there's been a lot of experiments since the 90s, as I mentioned. Sticking, colliding, fragmenting. This one is a nice bouncing one. These are millimeter-sized grains, and we have lined up the two grains we're looking at. Oh no, this is nice sticking, sorry. So this experiment had a lot of bouncing, and two of them were sticking. So, yeah, so it's tricky. You have to have statistical data, which is basically what I want to say next. So that one, here we had growth of particles also on a suborbital rocket. This is a processed video where we only see the growing aggregates. So that worked pretty well too within 3 minutes. All right.
But all that produces more like a sintered material. It's not melted together as the larger rocks appear to be. There's a difference in density.
Yes, we produce what is called an aggregate, and it is not a rock. We're not producing rock, we're producing aggregate. So then there's several next steps to go to the rock. Either heat events, which we think happened for the chondrules, so that the chondrules were these fluffy aggregates that went through a heating event, a flash heating event, or compression events. So you can compress, for example, with bouncing collisions until you have an actual more compact object. But we're looking into the growth itself, and we're actually trying to have it as similar as possible to the protoplanetary disk. So there, if you have gentle collisions, you will have fluffy aggregates. If you have more violent collisions that are not too violent, you might have compaction of your aggregate. So in any case, sometimes at the same speed they stick and sometimes they bounce. So there is a transition regime, and in order to understand that transition regime, we need statistical amounts of data. So we need a lot of collisions. The experiment I showed, we used to actually manually track each particle and see if it was bouncing or sticking, but this is just too much work. We want more data, and we don't want to track it manually. So we went into some sort of new concept. We want long duration microgravity to have a look at a lot of particles, and we want to analyze them statistically. So for that, we have to go to orbit. Problem is very expensive, long development times of the hardware. Maybe your hardware then doesn't work, then you wasted 3 years of your time. So we ended up miniaturizing our payloads. Okay, so miniaturized payloads, they will be less expensive, they will have shorter development times, You can enslave students to make them. Okay, so one of these I'm presenting here. It's called NanoRocks, because we flew it with a company called NanoRacks. And this was in the early stages of commercialization of space. This company basically offers slots on the space station. They're small, but at a price that a university, for example, could afford. And you can buy the slot and fly your experiment on the space station. So with NanoRacks, we flew NanoRocks. Ta-da! So here we put several types of particles, different types. Some of them were coated with chalk in order to change their surface properties. And then some of them were smaller. These are more like 100 micron, and these are more like 2 millimeter sized. And the blue ones are millimeter sized. So we had a small range of sizes and a range of surface coating and a range of densities. And it went to the space station for a year and a half. And so here's what it looks like. I have to move a little bit. So at our tray that I just showed with the particles, that's the tray there. Particles are seen from the top. And the tray is sitting on springs, and we grab it with a magnet in order to shake them, because as it turns out, particle systems are very efficient at damping any type of kinetic energy that you put into them. So you have to regularly provide new kinetic energy to observe collisions, or they're just going to damp the energy, form clusters, and that's it. And at the top, of course, we had some light and a little camera that was producing the data. All right, what I just said. The camera, the lights, and the tray with the particles. All right, and now here are the particles that we put, and I get this question a lot. Why do you think that acrylic particles are representative? Oops, sorry for so these are acrylic, the red ones are acrylic, and the blue ones are glass. So why do we think that acrylic particles are representative of what one could find in the protoplanetary disk? And that's because they have a density close to the density of water ice. So here we're not intent on exactly reproducing the particles that are in the disk, but some of their properties. And also make our life easier, because if we want to put water ice in there, we need a lot more hardware. So these acrylic particles, they have density of water ice. The glass particles are actually pretty realistic. Silicates are very common in the dust that is found in protoplanetary disks. And then we had copper, which had a higher density, which represented more of the metallic component of the disk. And this is what it looks like. Here I have to exit a little bit, sorry. This no longer videos work. This is the kind of data that we get. Ta-da! So here you see the shaking event. We grab the tray. So we input a little kinetic energy, and then we observe how long it takes the particles to damp this energy and what they do. Do they cluster? When and how do they cluster? It doesn't look very exciting, but we're getting stuff out of it. And so many efforts.
How many times did you repeat that?
How many times we did that?
Yeah.
Yes, that's a very good question. I actually have it on the slide. I mean, in this particular case, 157 times, I think. Ooh, wow. Nice slide. All right, sorry. I'm trying to talk to my computer. We're stuck with this beautiful data.
It looks like the copper ones have good results.
There we go. Have the what?
The copper, the ones with the copper in it, looks like there's a lot of sticking.
So actually we saw most sticking with the dusky ones, the smaller, dark ones, as well as the ones that were covered in chalk. How is it? Okay, here we go. So these are 60-second long videos, and we had 157 videos. at the end of our experiment. So this was a lot of data. So we went into no manual tracking. We went into new types of data analysis. So as I just mentioned, there's two types of things that we're looking at. On the left side, we're looking at how well the system of particles is able to damp kinetic energy. So kinetic energy could be brought into the system by gas turbulences, by perturbances due to the presence of an early planet in a gap, for example. So all the particles next to it that are still in the disk would be perturbed. So you could have like input of kinetic energy like this, and how well does the system damp this energy? Or because if you keep the energy going for a long time, you only have bouncing, you don't have growth. Only when you are efficient damper of energy are you able to go into the next phase, which is cluster formation. Once your energy is damped and you reach very, very low relative velocities, you start having the formation of clusters. And then we looked, when did we see these clusters form? What kind of clusters were they? All right, let's start with that. So here, for example, from data analysis in our tray with the little red particles, the ones that had the density of water ice, we have initial average velocities of 4 millimeters per second, and within 20 seconds, it's all damped away by collisions. So each collision is slightly inelastic. You have many, many collisions. It's very efficient at damping your energy. So there you can get a coefficient of restitution for your different types of particles. We see that, so coefficient of restitution is how well do you damp. If you're close to 1, you're not damping energy at all. If you're very low, you're basically almost sticking to each other. And so we see that particles had different types of behavior. Back here, the 3 back here that are lower than everybody else, they were with this dark dust. So that dark dust was very sticky. The copper actually was rather non-sticky. And there's the big planetarium piece here, I don't really see that. So this is what we're looking at, and we're looking also at cluster formation. So here's an example what we do with the data. We measure how many clusters and what's the average size of a cluster. And so here again are ice particles, so to say. They were forming an average clusters of 5 particles. And here we have 2 clusters of 5, and it looks like 1 of 10, but that's a bit of the perspective. If you look at the video, you see these are 2 clusters of 5 particles. So we measure that, and we measure when exactly did that happen, for which speed. And here are the speeds, and then we put them in our model that we had earlier, and we see that for these velocities that we measured and for the mass of these aggregates, we actually fit this transition from sticking to bouncing rather well. So this transition was computed manually, and now that we have statistical data, we can say from the data that we collected, this model actually works pretty well. So we can basically confirm this recipe can be used, so this transition here can be used in larger simulations that will simulate the entire disk. So what does this say? So let's get back to our problem of how we actually form the kilometer-sized body from these centimeter-sized grains. There's 2 theories. The first one is called the few lucky ones. So in this idea, you have the bouncing, you have the fragmentation, but by chance, because you have some statistical, you have some tail to your distribution of what's happening, a few of the particles survive, and they now feed on the fragmented small grains from the other collisions that did not survive. Because if you have very fine grains and you have a very large one, the fine grains are just going to agglomerate on the large one. There you have growth basically feeding from other fragmenting collisions. The other idea is that there are some concentrations of particles due to the gas having either instabilities or having vortices, for example, turbulences. So you would have concentration of particles due to the motion of the gas. The gas carries these small particles with it, and if you have a vortex, for example, it would tend to concentrate the particles in this vortex until the cloud of particles is big enough to collapse under its own weight. These are the two leading theories. Yeah, question? All right, so here are like simulations for the few lucky ones. So VD is velocity distribution. So if you add, these are your grain, how many grains you have. So like a lot of grains, not a lot of grains, and this is the size of the grain. So here you have all the grains that are smaller than 100 grams. Then with time, you see that you can actually form grains that are 10 to the 10 grams if you have a velocity distribution. The velocity distribution represents the size difference between the grains. You have very large grains, very small ones. Small ones are coupled with the gas, and large ones are not, so you have difference in velocity. And so you're able here to create populations of grains that are much bigger, so reach a kilometer size. On the right side, and that's a video again. On the right side, that's a simulation of how dust can concentrate due to gas motion. So dust is blue, and as the dust gets more and more concentrated, it gets more into the red and yellow colors. And this is just looking at the disk from the top. So this is a portion of the disk. We look at it from the top, and with time, the gas has these instabilities. It creates these concentrations of particles, and now you have basically these clouds of particles that are rather dense that start looking like bodies. And these clouds of particles are still, they're just like a concentration of particles, but if they get heavy enough, they can start having their own gravity, and you have a collapse of such a cloud into a small body, a kilometer-sized body. Okay. So the few lucky ones. This is really no. Here we go. A few lucky ones. If this is what you think is happening, you would get very compact planetesimals. So planetesimal is a baby planet, like asteroid sized. So you would get a very compact, very dense planetesimal. Also, simulations show that this would take a very long time. This is problematic because we see disks that are like million years old, couple million years old. They have the dust. We see the dust, and poof, starting 10 million years, you don't see any dust anymore. So the planets must form very fast, basically. So the problem with the few lucky ones is mostly the compactness of the planetesimals that you get and the very long formation times. The other theory, the streaming instabilities, the concentration of particles, that's a very short formation time scale. It has a very short formation time scale. You get so-called rubble pile planetesimals. That's basically a very fluffy asteroid. You have just grains that were pushed together. You have a very low density body.
Would that be like Bennu? The asteroid?
Yes and no.
Oh.
So yes, because Bennu is, we think, a rubble pile, and no, because what happened with the asteroid belt is that after they reached kilometer sizes, they had a very strong collision period. There was a period of time where all asteroids were colliding with each other, and then what happened is that there was a lot of fragments, and these fragments then reaccreted to make these rubble piles.
So you can't get any useful data or observations from.
Yeah, you can, of course, but more from the so-called primitive asteroids than. So for Bennu, I think that what they see on the surface are basically fragments from the period of collisions in the asteroid belt. If you want to see very pristine bodies, where you want to go is the outer solar system. If, for example, Mu69, that is most probably something that has formed like it is right now, and its density it is like fluffy. It is I get a rubble pile from accreted fragments is also fluffy, but the fragments are not the pristine original parts anymore. But in the outer solar system, or some of the comets that come into the inner solar system, you have the more pristine body there. Alright, so basically just, if you concentrate these particles, they will end up collapsing under their own weight, if you get enough to collapse. And again, now it works. So just again, and this is just a couple of orbital timescales. So this is a very efficient process. And it creates very fluffy planetesimals. So right now, the leading theory. So how does our data contribute to that? So if you want to concentrate your particles and have them collapse into one large aggregate, you have to have very efficient energy damping inside of your cloud, because the potential energy of the cloud gets transformed into kinetic energy as the cloud collapses. And so if this kinetic energy is not dissipated, you will never have an aggregate. So if your system is efficient at damping energy, you can create your aggregate. So this is how basically our measurements can contribute to help understand if this is possible or not. So the collisions that we see are very efficient at damping energy, and so such an aggregate could form by collapse of a cloud of dust particles. Here's a picture of a slice of a primitive meteorite. So so-called primitive meteorites, they have not been differentiated. We think that they hold clues to the early solar system. And these primitive meteorites, they're basically composed of these millimeter-sized inclusions, which are the chondrules, embedded in a dark matrix of micrometer-sized grains. And so this does indeed look like if you were to take a bunch of these millimeter-sized grains and just compress them together. And now with time, of course, it becomes sort of more of a rock, especially if it falls through our atmosphere. It creates a crust, it becomes very hard. And if you cut it, you can see the history of formation of this primitive meteorite by how it's put together by these balls, these aggregates. So we think we're on the right path with that. All right, and because we want more data, and it's just to show you a little bit how we spend our time, we decided to do a CubeSat just to collect more data. So instead of trying to go to the space station again, we decided we were going to go to orbit. So a small experiment into orbit, that's a CubeSat for us. And so we decided to put our experiment in one of these smokers. So this is about 30 centimeters, and I'm sorry I'm talking metric all the time. So it's about the length of my forearm. And you see it's a 3-unit CubeSat, each of these about 10 centimeters, but you can make them in these several unit formats. And NASA funded this, and we're supposed to fly to in March this year, but who believes it? Not me. The first flight date was end of 16, December 16. Yes, we started the project in 15. Virgin Galactic are the ones carrying us to space. And this specific vehicle that is going to do that has never been done before, so they went into a couple of delays. So that gave us time to finish it, but now it's waiting. It's waiting in the lab. So it's going to be up there 3 years, and we hope that we can get an experiment run done every 2 weeks, approximately. So that will give us more and more statistical data to see if we understand well this transition from the sticking to the bouncing regime, if we understand well the formation of these aggregates. How do we do that? We put particles in this tray, And then we put the tray on springs again, but this time we will be shaking it by poking it from all three sides. And that's these solenoids here. That's how we input our kinetic energy. And then, oh, this is what it looks like. So we try to hit size distribution. So these are centimeter size, these are millimeter sized. These are glass, so that's a density distribution here, and these are our acrylic water particles again. And then we have a camera on top that looks at them. And all other batteries and boards for telecommunication, because we have to get all of our data back. And finally, this CubeSat is ready after so many years.
You have one of my former students.
Which one is it?
It's Trisha.
Yes.
Joseph.
Excellent.
Big Star Trek fan. That's
yes.
cool that I recognize her.
That's true, yeah. Very good. Well, perfect. She went from engineering to physics. Very proud of that.
Very sharp mind.
Yes. Yes, she helped a lot. Look, we all look so tired. Yes. But great experience working with the undergrad students.
Collisions will tire you out.
Yes. Yes. And hating the CubeSat also. Anyways, so it's ready to go. Here we 3D printed an encasing just for it to stand there and wait for Virgin Galactic to be ready. So the next challenge, we think that icy collisions are very different. Maybe not very in the principle, but very in the measurements. When does it start sticking? What kind of aggregates can we form? Icy collisions, particularly starting a certain size, we're not sure we understand them all, because really it's very complicated to do cryogenic experiments, so not many experiments have been done, and also we haven't really visited the outer parts of the solar system yet. We're much better informed about asteroids, but as I said, the asteroids went through a phase of violent collisions between themselves. So the more pristine bodies are probably out there in the trans-Neptunian region. And we have now visited one with the New Horizon mission, and it's absolutely amazing, because we think, or at least I think, that we see the very building blocks. So we see some of these units here. So we see first two main units, so that would have been a very gentle collision between two kilometer-sized bodies. But the kilometer-sized bodies themselves are made of sort of meter-sized units. And when you go down closer, so not on this one, but on the Comet 67P that was visited by the Rosetta mission, you see subunits. On the meter-sized units, you see centimeter-sized units. And if you get even closer, because the lander was alive for a bit while going down, you see smaller and smaller grains composing these. So the next challenge would be to understand how icy bodies out there formed, and these icy bodies probably hold really pristine clues to how this process was formed, better than even the most primitive asteroids. Although I have to say, the slice of meteorite I showed earlier is pretty good already. So thank you. I hope this went out to you. I'll take questions. I'll go back to give the mic.
Oh, you need questions.
Yes, questions.
Can nucleation have any kind of effect, like between the particles and the gas?
How did you say?
Nucleation.
Nucleation. What is that?
Where it forms where you form a gas bubble on a grain that has an irregular surface. And I'm just curious whether or not a gas bubble can produce like a cushioning effect.
So I don't know. I don't know that we've done any work on that. But what's been worked on is if you have gas. So if your small aggregate is moving through gas, you have a layer of the gas that can trap incoming smaller particles better. So there is an effect, a back effect of the aggregate moving through the gas on the gas, And this gas now has an effect on the motion of other particles that has a tendency to help the accretion. So there's been work done on that the gas close to certain of these small aggregates does play a role in enhancing the accretion.
You're talking about a gas being created because of collision?
Not just because of the volatiles that exist in the planetesimal in the protoplanetary disk that they just are trapped from.
And the disk is mostly hydrogen, and then there are some volatile, what we call then volatiles like argon, oxygen. So some of these are in the gas form in the disk, and when they get trapped, and you see them, for example, on the comet 67P, that means you have very pristine material because these are very volatile. They want to escape. So if you see argon coming off of the comet, that's because this argon was trapped in the very beginning when the gas was still everywhere.
When you're talking about dust, are you talking about mineral dust?
Yeah. So it depends who you talk to. Some people will say just anything that's not hydrogen and helium is a metal. Yeah. So typically for us, it's like minerals. It's silicates. Yeah. So these silicates that includes these olivines. They have some magnesium in them. Forsterite. So silicate derived, and then you have the metals also, the actual iron. So these are the types that are very common and that we use as similants for dust.
When you have the cutaway of the meteorite there, you've got a combination of what, aluminum, your nickel, your irons, that sort of thing.
So these are rather metal poor. There are some of these atoms inside of the molecules. The metal starts being seen when you start having a differentiated.
Older.
So some of these fragments, some of these meteorites we're getting are just metal, like iron, nickel. So these are from like a body that was large enough for the differentiation to happen, and then it was fragmented, and some of this core that had most of the metal ended up being this meteorite. And then you have the rocky ones that are very metal poor, they're from the crust. And then actually these primitive, they have some of the metals but not concentrated in any way. Yeah.
Since a lot of planetary disks come from the remains of like previous events like supernovas and dying stars and stuff, is there scenarios where a lot of large objects could already be there?
So I think you mean more accretion disks or debris disks.
Okay.
So the protoplanetary disk specifically called like that because it's around a young star, but we see debris disks around objects like other astronomical objects like accretion disks in particular around black holes, debris disks around older stars. So there, I mean, the debris, yes, it could be that it was something, and then because of the central star becoming maybe larger, more dense, or accreting from its binary, because binaries are very common. If you have an increase of mass, then your Roche limit maybe moved, and your planets basically got torn apart, especially if they were rubble piles to start with. So debris, or you went through a collision period in the history of the disk, like the asteroid belt, for example. So yeah, debris disks could be debris from larger bodies. Yeah.
About supernovas.
That's it.
When it gets blown out from supernova because of radiation, does it become sterile?
That's not from you, right?
next month, join us from okay, on David.
All right.
Okay, thanks for hosting me.
Thank you, Joey. That was great. Okay, so next, before we take a break, we're going to talk about upcoming events. Slight change of projector systems. You have a quick one while we transition? Sure.
Okay.
You
When
have
was
the
the
mic?
last year in the newspaper, there was an article about an upcoming event. Let me see if I can find it. Oh, here it is, Bach Tower, at the end of the month. All right, so we've been going to Bach Tower for several years now.
During AstroFest?
Yes, it is. Saturday, January 25th. And it's got a number of speakers on there. Let's see, one of them is some guy named Demeter. Appearing at 7 o'clock. So write down all your questions about the universe, because he's going to be solving the mysteries of the universe. Just for a note.
One puzzle piece at a time. There's billions of them.
There you go.
Okay, thanks, Eric. So that is not on my list of upcoming events. And if I've missed anything, please speak up. This weekend we have telescopes at Trotwood Park. Then we have the Seminole Star Party at the gun range at Geneva. Derek, do you want to say anything about that? It looks like 2 nights.
So the 18th, so it's actually into the 18th is a Saturday, into the 19th, because technically we're going on a little bit later. So it's actually only one night. So yeah, so it's going on after midnight, so I guess that's probably where the 19th came in there. Yeah, so we're going to be over at for those that haven't been to Geneva, basically the driving track that the police forces here at the college do their practice on, it's really, really expansive. And it's a great place for setting up telescopes and things like that. We're going to be doing a big event there with telescopes. We're also going to be having the classroom space open for doing presentations. So right now we're still finalizing some of the speakers, but we'll be initiating that, releasing the schedule on that very soon. But essentially it's just a night to go out and enjoy being under the dark skies of Geneva. So we definitely would like for you to come out there and set up your telescope and just have a good time. So we'll be setting up probably around 4:30, 5 o'clock. We'll be opening the gate around there, and you'll just come on in, and we'll set up your telescope in the driving track. We'll kind of do it in such a way where it's a line almost. Usually you park your car next to your telescope, and then we'll have a nice line of telescopes that people will be able to come visit. So it's a very relaxing, kind of low-key event. Usually we have about between 30 to 100 people at these events, and we're looking to hopefully get a little bit more than that, but that's still pretty good. It's a good, again, chance for you to just go out and enjoy the night sky. I'm sorry?
What time does it start?
6 o'clock to midnight.
Or maybe a little after midnight.
A little after midnight.
Yeah, if you haven't been out to the Geneva gun range, it's a pretty easy drive. Even if you're up late, it doesn't take very long to get back. Assuming you didn't drive from Tampa or something. Eric, do you have something else?
Power.
No, there's no power.
Will there be a private night for members on the 17th?
No, unfortunately, we weren't able to get approved for that. We will be doing events like that in March and April. It's spring is usually their busiest time of year, and we're kind of under the mercy of the Criminal Justice Department. But I will talk about a site.
Yeah,
that you might be interested in.
Derek's found some other places we might be able to go. We'll talk about that later. So AstroFest coming up the 23rd through the 26th. The 26th is Sunday. That's the last day. So Thursday through Sunday morning. If you haven't RSVP'd or paid for it yet, I will be up front during the break to take your name and money. I don't know if you got the email, but we do. If you're already a member of the Chiefland Astronomy Village, you don't have to pay the $25 fee, but there's a $25 fee to join that. That fee is good for a year, though, so you can go up to Chiefland anytime once you're a member. Also, we have Coffee and Cosmos on January 31st. That's at the Lake Mary Starbucks. I'm going to do a sort of impromptu cell phone astrophotography workshop at the same time, and I'll talk about that a little bit later tonight as well. Also, the Lake Harney Astronomy Night, that was also on the calendar, also at the Lake Harney Wilderness area up in Geneva. And did I miss anything from anyone? Lynn, yes?
Yes, there's 3 school events that I've already mailed out the volunteer request on. The 14th is Demeter, and the 16th is English Estates, and on the 23rd, first day of our AstroFest, is the Orlando Science Elementary.
Okay, thank you.
Len? Orlando Science Center on the 18th?
Yeah, Orlando Science Elementary.
Okay.
Not the Science Center, the
No,
school.
the Science Center is having a Science Night Live on the 18th.
On the 23rd?
23rd? What is the,
Is that the adults?
yeah, on the 18th.
18th, yeah, that's up
Okay.
already, isn't it? Oh, no, it's not.
No.
Okay.
Lots of events, lots to choose from, some of them at the same time. And if you can be in 2 places at once, all the better.
Eric's gonna do that between Black Tower
Right.
and...
Yeah. Eric, are you coming to AstroFest?
For the first Thursday and Friday, but I'll have to leave on Saturday to get down
Okay.
to Buck Tower. Yeah. Actually, I'm planning to be there a whole week. From Monday
The
through-
hours for the February the 15th event would be, what time is that, Derek? Do you know?
Sorry,
Lake Harney?
Lake Harney is 6 to 6 o'clock runs to like 9:30. It's not a very long event.
Okay, thank you. Okay, so we'll take about a 10 to 15 minute break. There are refreshments in the next building in room 135. And if you haven't signed up for AstroFest, what's that? Oh, 136. All right, if you go there and one room is locked and the other one has refreshments, it's the one with refreshments that's not locked. Okay, just in case. Everybody's so rowdy. Man, what were they serving over there in the snack room? I missed out.
That kind of thing to me. I always bow.
So, okay, so we have, that's pretty great. If you haven't signed up for AstroFest yet, I'll stick around for a little bit after the meeting. Looks like we're going to have quite a few people there, so I'm very excited. All we need is clear skies. So, who wants to be in charge of weather? All right, make sure we have 3 clear nights, nice and cool and dry. That works great too. Is there a rule on generators?
Yes, you can't have a giant generator running all night long.
Yes, you can't have a giant generator running all night. They have power, so you should be able to plug in and have power. I usually run my my gear on battery, but it's nice to have power there anyway, just in case. Do we have a place to watch movies? Yeah.
I mean,
my tent? No, it's going to be tight. Very tight.
there's a movie theater about an hour in Crystal River.
Okay, yeah, there's a movie theater an hour away. I will have every episode of Fireflies on my laptop. So if we get really, really desperate, we can have a Firefly marathon. Denise? Oh yeah, absolutely. Nobody buying ban. Nobody buys any new equipment between now and the end of the month. You got it? Or else.
Once you use that, or when you have it, and we have to cancel, you can use it for your membership this year. Like if you pay $45, we pay some of it.
Oh, so you're still a member of Chiefland, so you can go back for a year. Yeah, that's a good point.
Yeah, but also for your membership here, you could use if someone was an RV, instead of refunding, apply for the membership.
Yeah, we probably won't do refunds unless there's like a hurricane coming. We're going regardless. We're going to do radio astronomy. All right, so time for our mini programs. Anna Metke, who is our education chair, is going to talk about space dirt. Everybody likes space dirt. That's a cool topic.
All right. So not so much necessarily about the space dirt, but I know you guys are always excited about it, so I brought a sample. So this is our Lunar Highland simulant. You're not supposed to shake it. It's going to stick to the jar. You won't be able to see it.
Trying to make a planet.
So anyway, last semester I did like a really easy backyard kind of research project, and I just kind of wanted to share some of the kind of interesting facts I learned and hopefully encourage some of you to go out and do some easy science that doesn't require expensive equipment or anything all the time. So basically, we see the moon, and it's got all these cute little dimples on it, and we wonder to ourselves, like, how did this happen? And we know that there's a lot of collisions going on, but what does the collision look like to make that happen? Next slide, please. So yes, this is our question. Next slide, please. Do you want to give me a clicker?
That's all good.
Okay, we'll just keep in touch. So basically, the experiment was extremely straightforward. We have dirt, we have a projectile that could also dual as a weapon if your lab partners get mean. And so the projectile had 3 different launch speeds, like 3 different spring settings, so the spring launcher, and then we also varied the angle that we were launching from. So basically we wanted to see how does the eccentricity of the crater, like the ellipticness of the crater change, and how does the depth of the crater change based on these parameters.
What were you using for a projectile?
It was a good question. It was a little steel ball.
I thought it might have been a potato.
A potato? No, maybe next time, There's a lot of potato-shaped asteroid things.
It's
Next slide, please. All right, so basically we used some basic relationships to kind of do some calculations, figured out which velocities that were coming out of the launcher, and we did hours and hours and hours on math to figure out like the kinetic energy, the momentum, and we wanted to see how did all these things relate to the depth and eccentricity of the craters. Next slide, please. Also, there was a lot of math, but it was all very basic algebra. So we just used like straightforward kinematics and stuff. So nothing too crazy. So we know that energy is conserved, so all the kinetic energy and potential energy from the asteroid would, or from the projectile in this case, would get converted into kinetic energy as it hits. So I'm gonna have to stand somewhere else. So I got to learn a little bit about the theory of crater formation, which is actually really interesting. It comes in like 3 different stages. So the first stage is called the contact stage or compression stage. So this is when the projectile gets into immediate contact with the soil and basically forces shock waves through the soil. And then the second phase is excavation, which actually kind of like creates the hole, and then ejecta comes flying out everywhere. It's a big mess. And then afterwards, the modification is kind of like the cleanup, the after effect. So after the crater is formed, and then the ejecta kind of settles, and then the sides kind of collapse in on themselves depending on how much gravity is in play. Next slide, please. All right.
Then we can point stuff too.
Ooh, I know, it's pretty straightforward. So there's also part of the theory of crater formation gives a cute little formula that, so the D in that formula stands for diameter, the E is the energy, the K is just a constant based on like the mass and properties of the projectile. And then the N up there is what we're curious about, because the N up there is what tells us how much of the energy is getting transferred as ejecta. So on the graph you can see, so we graphed the log of the diameter and everything, and we found that that's apparently kind of a high coefficient. So we were getting a lot of ejecta, so you can see in the picture. So scientists kind of call that a lot of ejecta. So that's kind of interesting. All right. And then, so of course, we also had we found all the basic properties that you were kind of expecting. So we found that the velocity in the vertical direction had a lot to do with the depth, not so much in the horizontal direction. And of course, this is, in agreement with Newton's second law, as we know, F equals ma. where force mass acceleration, and as the projectile gains acceleration and it impacts the regolith with a greater force, leaving behind a deeper crater. But it was kind of cool to see how you can see that even with like your own measurements and everything. We checked out the momentum and landing angle and those relationships with the characters of the crater. So we saw, of course, that as the landing angle increased, we saw more depth. Yes. So as this is kind of hard to visualize. So if the landing angle is, the launching angle is small, the landing angle, if the launching angle is small, it kind of hits the soil from like the side, so that creates a lot more eccentricity, so you see like a more oval-shaped crater. And if it has a high launching angle, it kind of hits it from above, so you see a lot more deeper craters and not very elliptical craters. And then, of course, in the momentum, we saw a strong correlation of momentum in the x direction, so like in the horizontal direction, it correlated a lot with the eccentricity of the crater, but not so much in the y direction. And that's pretty much all. It was just a little bit of science, a lot of math, and it was a lot of fun.
Does anybody have any questions for Anna about her science experiment?
Wait, where's my dirt?
Yeah, don't, here it comes, here it comes. Give it to me, I'm gonna shake it up some more.
We have the dirt on you. Is there anything
How expensive is
special about the dirt?
Is there anything special? Tell me about the dirt.
Well, to be fair, Richard, you kind of stole my thunder there, but, sorry? Yes, so this is our lunar highland simulant. So it's a lunar simulant, but it characterizes pretty much like the lighter parts of the moon. We also have a Mare simulant, which represents like the dark, more sea parts of the moon. So this is a mineralogically and particle distribution accurate simulant of stuff on the moon.
More dense than the other, because that's pretty heavy.
They're both pretty dense, but the Mare one is a lot fluffier. So
Ideal for
yeah, and actually my next research project is to study the electrostatic forces.
Who's we? Where does it work? Not what I would have thought.
Oh, this is from the Exolith Lab, which is basically a lab funded by, or kind of self-funding because we sell this stuff, but also with the collaboration of Florida Space Institute and UCF. So kind of where Julie's from. Yes, sir.
It's kind of heavy.
Yes, it is kind of
I'm just
heavy.
wondering how much it is.
How much is in here?
No, how much is worth it?
How much it's worth? It's $25 per kilogram for now. They hired me to do some business analytics for them. I am telling you right now that our Mare simulant is going to be very expensive very soon. Buy now.
The price is going up, you say?
Oh yeah. For maybe not so much this one, but some of the other ones, yeah.
It's land, land always goes up.
clients that would buy that.
Yes.
All right, and how much would they buy?
Okay. So a lot of my job is to make this stuff. So what we do is we take big rocks, some of which we collected like from mountains in Montana, brought them back here. We take these big rocks. We used to sledgehammer them into smaller rocks. And then we used like a small rock crusher to bring them down to like a fine powder, kind of like you see here. We've upscaled a little bit. We got this big rock crusher that can crush our boulders for us now, so I'm a much happier worker. But yeah, so basically that's kind of the process. And then we have different materials. So we find different materials that mimic different mineralogies, and then we mix them together after we've crushed them all up based on how much is needed.
Another question.
Yes.
You're saying the price is going up, so can you be outsourced by China?
Oh, I'm sure eventually. I know that, but they have purchased some of our stuff, but I'm sure they're just trying to make their own. But yes.
Which simulant did you use for your experiment?
This one here, it's the Lunar Highland simulant. Yes. Yes, other than humidity and whatever, it's dry. Also, we make it by tons, like UAE just ordered like 250 kilograms of a bunch of simulants. NASA's ordered like half tons of simulants, and ESA.
So when
all
they
these
do
guys.
like lunar crawler or Mars crawler,
Exactly.
run it through their skeleton, still
Yeah.
making rocks out of that.
Yeah, so
Yeah.
yeah, we actually for our asteroid simulants we mix them with water and then dry them and then make clumps, kind of like different aggregates, kind of like the balls Julie was showing. Those were probably made in like Exolith Lab 1.0, previous to the fishiality. I saw a bunch of hands. I hope I answered every question. Yes, sir.
I was just wondering, like, how do you know that you're making like a close simulant? Do you guys actually have like a sample of moon dust? Or?
Great question. So, kind of yes and kind of no. We, as a collective, scientists publish data. So they tell us this is the stuff we found on the moon. We can analyze it, and then we can mimic it. For Mars stuff, we mimic what the Curiosity rover and other like UV spectra that comes back that tells us this is how much of each mineral is here.
So you guys do Mars too?
Yeah, we do Mars, except for the problem with some of our Mars simulants is that there's a lot of like carcinogens and stuff on Mars, and you know we're not trying to die, so.
Lunar dust is pretty dangerous too, isn't it?
It is, great question. We actually are just kind of like finished up a huge cleaning. We are under new management, and we are cleaning, and it's awesome.
So is there actually a risk to you guys in simulating?
Absolutely, there is. Yes, so it's actually very dangerous. So this is why we're becoming much happier workers now.
What's
Yeah.
what's the name of the lab again?
Exolith Lab.
Okay.
Yeah.
And what is the danger?
So it's because a lot of the particles are so small, and we also work with some silicates that are really dangerous and carcinogenic.
So you have to wear protective clothing and masks.
Yeah, so we wear the masks. We've really managed a lot of our dust. That was like a huge project for us. So it's not as dangerous, but it used to be like you walk into the lab, it's hazy, and like you can feel it in your throat in 5 minutes. Yeah.
It's insoluble too.
Yeah. I mean, but you know, finally someone did something about it, so that was nice. Yay. All right.
Well, Marie Curie won a Nobel, so science has a price.
One last question
Yes.
involving the simulations, that you guys do. Because I noticed up here it said melt, like the object itself also gets destroyed when it impacts. Are you guys because you guys use a little, not up there, but in the graphs you had before. And you guys are using like a little steel ball, which I'm assuming is just fine after the impact. Do you guys consider using impactors that will also disintegrate, like to simulate that better?
Oh, absolutely. So yeah, so this project I did was just for like research credit for our class, but the like science research, there's so much going on right now, and there's a never-ending list of research that's going to continue happening. Stay tuned. All right, thank you, everyone.
Okay. Next up is I believe we're Astrophotos.
Yeah.
Yes. Derek's gonna drive for that.
All right, so there's not many photos this month because for those that have been paying attention to the weather, we've had a deluge of rain, which means that somebody in this audience had bought a lot of Christmas gifts for somebody in astronomy.
It was Lynn.
It was Lynn. I knew it. Okay. No, So unfortunately, many of us haven't had the opportunity to get out and do some photos, but we do have a few. We have only 3 to this month, but these are really great nevertheless. So let's go ahead and start with our first piece here. This, I believe, is Richard's.
So this is Plato, the crater Plato in the middle there with the shadows coming across very prominently. This is called the Plato Hook. And those shadows are only visible during some months due to the libration of the moon. The angle's going to have to be just right for that to pop out. This is a really excellent example of one of my first principles of astrophotography, which is everything looks great on a cell phone. If you zoom in on this, you can see quite a bit of compression artifacts and noise control that the iPhone adds. And I'm not apologizing for it. What I'm pointing out is this was taken with a cell phone on a telescope in the parking lot at Starbucks. Someone asked me if I would do a workshop on cell phone photography, because that is a highlighted feature of our Coffee and Cosmos events. People bring their cell phones up and I help them take pictures of the moon. And I really don't think it needs a whole workshop, because there's not really that much to using a cell phone to taking a picture through the eyepiece. But there are a few tips and tricks other than having a bracket to hold the phone separate. And so at the next Coffee and Cosmos, I'm just going to invite you, come up, bring your cell phone, and we'll do kind of a, if not a workshop, and a hands-on tutorial. And I'll show you a few tricks to help you get the best, at least the best lunar photos with your cell phone through a telescope. That's it for me.
All right, thank you, Richard. All right, next one I think goes to John Pinto. John, are you still here?
Yep.
All right, so this is, I believe, during your experience, speaking of cell phone photographs, this is another one of the moon taken during Coffee and Cosmos, correct?
Yep, and if you look at Plato, you can kind of
Same
see the
night.
same shadows in there.
Yeah.
So there you go. So, again, you can see kind of, you can crop this, but, it gives you a little bit much of a bigger scale of the moon, so that's good. In the last image that we have here is Frank's. He was the only person in the universe in Florida to actually do some astrophotography recently. So I think he has I think he bought one of those cloud filters for Christmas. I think. Right, Frank? Is that what? Okay. So go for it, Frank.
Yeah, so with all the hype about Betelgeuse, I thought I'd image a supernova remnant. This one's called the Jellyfish Nebula. It's in the constellation Gemini. It's about 5,000 light years away, so quite a bit farther away than Betelgeuse. And they don't really know when this blew up, somewhere between 3,000 and 30,000 years ago, so if Betelgeuse does go pop, wait around a few thousand more years and it might look like that. This was about 7 hours of exposure time in narrowband from my driveway in Lunar Springs.
Wow. What did you use?
The camera was an ATIC 383L Plus with narrowband filters on a Paramount Mighty mount and a Skywatcher 190mm telescope.
And exposures?
10-minute exposures for total 7 hours.
So beautiful.
Thank you.
All right. So as you can see, hopefully with AstroFest coming up this month, and hopefully we'll get some clear skies, our February Astrophoto of the month should be filled with some amazing photos. So take it back, Richard.
All right. Actually, not going to take it back for very long. We're pretty much done, except I would like to invite our observing chair, who is Derek, to take the microphone again, to tell you about some exciting developments in. Well, I'll let Derek tell you about it.
Okay, so how many of you here are looking for closer but darker locations to do observing that aren't a pain in the butt where you have to get 7,000 permissions and need me to be there, some other person to be there, or whatever? Well, one of the things I like to do is explore and to really just search around the state, and sometimes your other hobbies lead you to some places that you never expect. So one of my other hobbies I've been focusing on the last couple of weeks due to the weather is fossil hunting and rock hounding, and there's a spot that I found some really interesting things in that arena. that led me to this site, and it's called Bull Creek Wildlife Management Area. So how many of you, by a show of hands, are familiar with Harmony, the town of Harmony? So for those, all right, so how many of you, by a show of hands, are familiar with the town of St. Cloud? How many of you are familiar with 190? Okay. So basically, we're talking south of Orlando, southeast of Orlando, kind of between, so kind of just south of the airport, about maybe another 40 minutes southeast of the airport. It seems a lot further than that is, but that's to give you an idea. But it's significantly closer to Chiefland, to Kissimmee Prairie Preserve, and the skies, for those that have been to Forever, Florida, are about the same. So southern skies are fantastic, great zenith skies, not too bad eastern and western. Your northern skies are your worst. It's pretty bad. It's obviously the Central Florida, Orlando metro area is north. But, you know, most of the stuff you want to look at is either in the zenith or towards the south, southeast, southwest. So you have a pretty good observing area to observe. Well, long story short, I finally got a chance to meet the volunteer, the person that kind of handles the check-in, check-out. It's generally used as a hunting area. But I asked the lady, and I said, hey, you know, I'm an astronomer. I like to come out and do astronomy, bring my telescope. And she's like, yeah, it's not a problem. It's open 24 hours. There's no gate. And for some strange reason, most wildlife management areas require a permit, but this one doesn't. It means that you can just, all you have to do is sign in and sign out. That's it. So in reality, this is a great place to go down for what we call ad hoc observing. One night. There are campsites there, but during the month of November through January, that's hunting season. So right now there's just tons of RVs and stuff like that, which means they're RVs, so there are electrical hookups or generators possibly. I haven't seen anybody running generators there though.
What
yes?
are they hunting there?
Deer, hogs, turkeys. No astronomers, no. In fact, actually, one of the hunters came over and, you know, was like, "Oh, that's really cool. It'd be cool. You know, it's a great place to observe and watch meteor showers." So they're quite aware of how dark it is there. But pretty much April through October, it's dead there. There's like nobody there. So it's a really nice place to get away. Now there is a bathroom, an actual bathroom at the entrance, and near the entrance there's this big field. That's actually kind of where I found those my rock specimens and stuff. There's a big open area where there's no trees. You can actually set up right there. The only downside of Bull Creek at that location is that you do occasionally might get a car come by every once in a while. But there are more remote areas as you get deeper in. Yes?
Well, as a female, part of my lack of being able to observe is as a sole female observer, I can't go where I know that it's dark sky. How safe is it if you want to go as a woman by yourself?
So the caretaker for the site is there most of the year, and she's a woman. So she's in a little RV, little camp, little like trailer over there. So she pretty much hangs out there most of the year. So she's by herself. But yeah, I could understand that. Of course, that's definitely a big concern. And of course, it's one of those situations where we could probably set up hey, I'm going out if you want to join me. That's a nice thing about Chiefland. Chiefland is great for that because you're kind of, that's another benefit about being a member of Chiefland is that it's a really nice, secure place. And I'm going to be honest right now, for Florida, I'm really disappointed because it was the perfect place. It was gated, it was dark, it was safe. Now, right now, the current update is that it's for sale. The property is for sale. However, according to the original documentation, it's not sold for development. It must remain wild. So whoever's buying it either is going to continue keeping it as a ranch or a wildlife area. So who knows what may happen. It may turn up to be something good, blessing in the skies. But for right now, it is closed and it's currently for sale. So unfortunately, this is the next best thing. in the location in terms of dark skies. So this is something that, for example, Mauricio, if you decide to go out, maybe you both can coordinate. But the nice thing about it is that you don't need to get a permit, you don't need to ask permission, and all that. So there's a little bit more relaxed in terms of setting up there.
That's a legit concern.
Derek?
Yes.
Which is it that's for sale?
Forever, Florida, which used to be our, it's a property off of 441 heading past Hullapaw.
I just skipped a beat there.
Is that where
Okay.
Old Creek is by there?
Kind of in that area. It's near Triple N in that area.
Is it?
Yeah. And, I'm sorry?
What's the name of the new place?
The new place is Bull Creek Wildlife Range. Yeah.
Has anybody used the old place we used to use, which is out here on I think it's 520 or something or other, but
The Lewis site?
huh?
Was it the Lewis site?
No, I don't remember that.
All right, you might be thinking of there was
Lone Cabbage Fish Camp.
Lone Cabbage Fish Camp.
No.
So I haven't heard of it. No. However, the skies are not as dark as they used to be over there. I know that the nice thing about this site is it's further south, far away enough from
This is
the
on the St. John's, and there's a boat launch area behind the restaurant.
Yeah, and unfortunately though, with the growth of East Orlando and all that development in Arcousie and Lake Nona, it's basically been destroyed with. But it could be a great place as an alternative. I might have to look into that, but definitely a field trip, go see how it is. But I do know that as far as the closest place we have to a portal site that is reasonable, this would be the closest. And but the caretakers have said that we can use that site, we can set up and all that. So and it's there's no permit required or anything like that. So this is a good location. The only thing is it doesn't have power, but of course in this day and age there are some really great alternatives now where you can essentially have power stations that are very affordable but also can generate a lot of power. So we thankfully live in a time period where there's a lot more options. But so that is the one bad thing, is that at the moment there's no place where you can hook up. Now supposedly where the hunting check-in area is, there are electrical outlets, so maybe I can work my magic and see if we can maybe set up somewhere where we could hook up to those. But I don't want to push it too hard right now. I just want to have at least a.
Do you have to make any reservations?
No. Well, for the campsite, I don't know about the campsite. I was just asking more of, okay, we want to come out here to do observing. You just get in there. There's a sign-in area. You just sign in. And and then you just check. I think there's a thing that says other or something like that. You can check that or whatever.
No, any cost?
And that's it. Yeah.
Any cost?
No, as I said, this is one of the few wildlife management areas that don't cost anything. If you go to Three Lakes, which is near there, you're required to have a wildlife management permit, and it's or pay a daily fee of $6. For some reason, Bull Creek doesn't have that requirement. I don't know why, but.
Derek, any chance we might organize an event, say in April, to just have the club go out there and check it out?
That's a great idea. I think we could probably set up something like that to go out and say, let's go to Bull Creek and set up. Maybe also introduce ourselves and all that. So yeah, definitely.
A couple of footnotes on Lone Creek, Lone Cabbage. First of all, it's a pretty good restaurant. Shrimp, raw legs, and egg tail. But the Deseret Ranch, the 7-county ranch owned by the Warrens, is to the southwest of there. And that's an extremely dark area. So some of the East County sprawl may not matter because of the proximity to that Deseret Ranch.
It could very likely be, yeah. So again, field trip. Let's set up something and go look. I do know another site that I'm trying to work with is Lake Kissimmee State Park. They've actually reached out to me as a potential investigating their dark sky site. They're actually in a very similar zone as Kissimmee Prairie Preserve in dark skies. The only problem I noticed that last time I've been there is they don't really have the very large prairie ecosystem where there's a lot of opening. Very wooded, but I'm planning to schedule a meeting with them soon to kind of go over and see what options we have. That could be another site as well. One of the biggest issues with Kissimmee Prairie Preserve, for those that have tried to book there, is that we are in what's the word? We're competing with Treasure Coast Astronomical Society and other ones, and there's only limited campsites available. So most of the campsites at the astronomy pad are booked all year long. Essentially, there's no they just literally just book the sites. So this has actually been, I had a meeting with the Friends of the Kissimmee Prairie to talk about this, and they still saying, hey, this is not fair. We need to have some other system where you can only book a limited number, but then have some available for others. And they're like, no, we don't want to do that. It's too much work. So, yeah, there you go. So anyways, it's not the greatest site. We had a beautiful site with Florida, but we're trying to find alternatives for similar skies, not as far as a drive, and hopefully, maybe this might work out. But doing my best to get, but we'll definitely try that other site as well. And there's a couple of sites I'm looking at in Brevard County as well as potential sites besides Biolab.
Thank you, Derek.
Yeah.
So I was struck by something. It doesn't matter what your gender is. It doesn't matter what your age is. Use the buddy system. Nobody in here should go anywhere remote by themselves. I'm going to share something very personal. I hope it doesn't bring you down. My youngest son, 20 years old, died alone in the woods with multiple attempts at 911 on his phone. Doesn't matter how old you are, doesn't matter how capable you are, something can go wrong if you're by yourself. It's going to be a very bad couple of years for somebody. So anyway, on that note, it's 9:30. This is a 2.5-hour meeting. We usually do not normally go that long. Thank you all for your patience. It was a very good program tonight, I think. And I look forward to seeing as many of you as possible at Chief One in a couple of weeks. So good night.